So welcome everyone to the virtual seminar on geometry with symmetries. So today I'll be introducing the speaker instead of Caroline due to bandwidth issues, but I hope I'll make as good of a job as she always does. And yeah, it's my great pleasure to welcome Gabriela Ovando from Universidad Nacional de Rosario in Argentina. Who will talk on first integrals of the geodesic flow on nilpotent groups of step at most 3. So welcome, Gabriela.
Okay, thank you very much. Thank you for the invitation, for this opportunity to Caroline, Emilia, and you, Ramiro, and also for the organization of this nice seminar. Well, you said I would talk about first integrals of the geodesic flow on nilpotent group of step 2 and 3. This is an outline of the talk. So I will give some motivations. Then I will explain about the symplectic framework. After that, we will see about first integrals. We study involution conditions and give some examples and applications. First of all, I will say that I am studying this topic for the last 5 years, and I am still studying this. There are several open questions for me, and I think also in the framework. People. Well, let us study with some motivation. I think several motivations for studying this came from mechanical systems. So the system of 1 degree of freedom you can see here in the beginning. So this is a differential equation depending on a variable, a real variable. One of the examples, more known examples of this equation is that one that describes the oscillations of a particle. And the general setting for this one is the differential equation that describes the motion of n uncoupled masses moving on Rn. And this is one of the basic examples of a completely integrable system, that solutions move on a torus, on n-dimensional torus. Another one, a known example is the rigid body problem, which is studied until now, and which has several investigation and research on this problem. But I would like to go to the first equation you can see here, because to solve this equation in general you will put an extra variable, okay, y. So you start with a variable x and you put an extra variable y. So you get from a system on R to a system on R2. And the question is that R2 is the tangent space of R. So when you put equation, the first equation in this way, you translate the differential equation of the first line on another equation on the 2 variables x and y. What you do there is that you can realize that R2 has a symplectic structure, and with the tools I will explain later, you consider a new Hamiltonian function for this, which is given here by the function h at the end of the beamer, and you put the kinetic energy plus the potential energy U where u is defined in terms of the f you put in the differential equation. And if you compute that, and you get the Hamiltonian vector field and the corresponding Hamiltonian equation for this Hamiltonian vector field, gives you solutions such that the solution of the first equation is put in this new solution on R2 now. So the point is that solution of the differential equations here at the first line translate into solutions of a system on R2, and those solutions are trajectories of the Hamiltonian vector field. And that is what the symplectic framework allows. But previously, we will start with other motivations on different topics related to that. I will like to mention some works on geometry related to integrable systems. For instance, the work of Dorothy Schutz about integrability of geodesic flows and isometricity, and some previous work of Caroline Gordon with Mao and also Schutz of symplectic rigidity, conjugate geodesic flows on two-step nilpotent manifolds. Patrick Eberlein started to study this topic of integrable system on nilpotent loop also. And that related to the geometry of nilpotent loop, more in two-step nilpotent loops, I should say, and dynamical questions, but other works on dynamics and loops were related more with Anosov diffeomorphism, as the works of Jorge Lauret, Cynthia Will, Mira Meingert, Tracy Payne, etc. So let's start now with our context, our geometry context. So we will fix for the top Lie group N with a Riemannian metric, which is invariant by translations on the left. So as we know, in this context, the geodesic equation on the Lie group can be written at the Lie algebra level, and we have what we call the geodesic equation on the Lie algebra, which is given by the equation we are looking there, where the T is the transpose of the adjoint map relative to the method, which is determined at the Lie algebra level. And as we say in the symplectic context, geodesics, that is, solutions of this equation, will be seen as integral curves of a vector field. So to start with that, let me recall how to construct this symplectic structure. So the cotangent bundle of a manifold has a natural symplectic structure, which is the differential of a canonical one form that you can read there at the third line. So this two form, as is the differential of a one form, it is closed and it is non-degenerate. But when the manifold you are considering has a metric, then you can translate this symplectic structure on the cotangent bundle to the tangent bundle. And so you have an expression for a symplectic structure on the tangent bundle of the manifold.
Excuse me, Gabriela, can I ask a silly question? Could you go back to the previous slide with the geodesic equation on the Lie group? Yeah, so what do you mean by that? Because I don't know, I'm having trouble understanding the equation.
Okay, this is when you have a geodesic, you can write the geodesic on the Lie group, So you write the velocity of this geodesic and you translate to the identity. So you can write this the geodesic as the left translation of a curve on the Lie algebra.
But on the right hand side there's an endomorphism of n, right?
Yeah.
And on the left hand side it's an element in n, so I don't understand how.
Because of that, you have the curve on n on the Lie group. Okay, you take the equation for the curve, and you see the derivative of this curve, and you see this curve as a translation on the left of a curve on the Lie algebra, and the curve on the Lie algebra should satisfy this equation.
Okay, that's an x. Okay, yeah, sorry, no, I wasn't.
It's the relation we have after the geodesic equation. You write gamma prime, so as a translation of a curve on the Lie algebra, and if you put the condition on gamma to be a geodesic, then the curve x on the Lie algebra should satisfy this equation.
Okay, thanks, Gabriela.
Yeah. Well, and then we go to the symplectic structure. Well, once you fix a Hamiltonian function, you fix a function, and we call this function a Hamiltonian, which is a function on the tangent space. Then, with help of the symplectic structure, you take the differential of the function n, h, and it is possible to construct the Hamiltonian vector field with help of the equation you have at the end of this slide. Okay? And so in the case of a Lie cube with the left-invariant metric, then the tangent space is trivialized as a product of the Lie group and the Lie algebra. And the energy, the function we will fix is called the energy function, which is half of the inner product of a vector y with itself. So it is easy to see that the gradient field of the energy function has the form 0y, and then the corresponding Hamiltonian vector field has the expression we can read here. Well, the gradient field is computed in the usual way, where, as you can see, we also take the differential, but we get the gradient field with help of the metric. So it's a vector field that we obtain when we put the metric instead of the Hamiltonian vector field. In most computations I did, it was easier to compute the gradient field and then to get the Hamiltonian vector field. But you can do the Hamiltonian, you can also maybe erase the gradient field and compute the Hamiltonian vector field. But for me, it's easier that to consider firstly the gradient field and then to get the Hamiltonian vector field. The point is that once you have the Hamiltonian vector field, then you can compute what we call the Hamiltonian equation. The Hamiltonian equation is the equation for the trajectories of the Hamiltonian vector field. So this gives you the Hamiltonian equation for the energy function, and that is written at the end. Okay, and there you can see the geodesic equation we previously read, okay, which is which is written in the second one. So now we have that the solutions of the geodesic equation appear related to the trajectories of this new equation, which is called the Hamiltonian equation for the energy. And that is what we will study, because the solution here will be seen in a certain submanifold that we will study. And this is the result of the Liouville theorem. But to get in this direction, let us introduce the Poisson bracket. The Poisson bracket on the tangent bundle of the Liouville is constructed with help of the symplectic structure. So once you have two functions on the tangent bundle, you compute the corresponding Hamiltonian vector fields, and then you will compute the symplectic structure on those Hamiltonian vector fields. And so the Poisson bracket is a Lie bracket on the set of smooth function of the tangent space that satisfy also the Leibniz rule. So a given function is called a first integral if its Poisson commutes with the energy function. And that means that the trajectories of the energy function will be constant along the function f will be constant along the trajectories of the Hamiltonian vector field corresponding to the energy function. Also, if two functions f and g are in involution if they Poisson commute. And that is what we will look for. That is, we will say that the geodesic flow is completely integrable or Liouville integrable if there exist n functions where n is the dimension of the Liouville, such that those n functions are first integrals, are pairwise in involution, and are functionally independent on a dense set on the tangent space. Functionally independent means that the corresponding gradient fields are linear independent. In particular, E itself is a first integral. So we always have at least one first integral for this system. And that is the point of the Liouville theorem that describes what we obtain when we have functions in involution, or functions that give us the integrable system. So when we have n functions in involution, we will consider the common level surface of the n functions. So we consider the set of point x that satisfy f1 of x equals c1, f2 of x equals c2, fn of x equals cn. And we will assume that those functions are functionally independent on MC. Then MC is a smooth submanifold invariant by the vector fields, the Hamiltonian vector fields corresponding to the functions fi. If this manifold is connected and compact, this is diffeomorphic to an n-dimensional torus. And in this case, one has more. One can introduce new coordinates, which are called action angle coordinates, and such that the first coordinates, or n of these coordinates, are in the direction transversal to the torus. The other coordinates move between 0 and 2 pi, and they set the representation of the torus in the form of product of n circles. And with these coordinates, you can rewrite the Hamiltonian equation in an easier way, and you can also rewrite the symplectic structure and to put the symplectic structure in the form of the Darboux theorem. Well, if the common level surface is connected but not necessarily compact and all vectors are complete, then the surface is diffeomorphic to a certain cylinder. This written in this way, this is from the book of Fomenko on integrability and non-integrability. So here is the question with this theorem is that you can see how or where the solution of the Hamiltonian equations are. They are in this common level surface, MC. Okay, in this context. So the first problem is to construct first integrals. Okay, we have one first integral, which is the energy function, but we need more. So several first integrals came from Killing vector. So when you have a Killing vector built on the manifold, you consider a function given by given by the formula you can read there. That is to consider the inner product of the Killing vector with the part on the tangent space. And this is known that this is the first integral. So when we look there, we know also that the Lie algebra of Killing vector fields is related to the Lie algebra of the isometric group. And so one possibility is to study this Lie algebra of the isometries of the manifold. Another family that one can consider is the family of invariant functions. So we will call invariant functions. With the Lie group N acts on the tangent space, on the tangent bundle by translations on the left. So a function f will be called invariant if it is invariant by this action, as you can see there on the formula. So the point is that when you will consider later maybe not the Lie group but the quotient of the Lie group, and you will translate to the framework of the symplectic manifold, of the symplectic structure and so on, to the quotient, to the tangent of the quotient, then the functions you get which are invariant will be easily translated to the quotient, to the tangent of the quotient. So it is important if you are able to construct invariant functions because of that. The Killing vectors are not so easy to be translated to the quotient. That is the problem in general. We will see some examples later. So whenever the group is nilpotent, then we have a good description of the isometry Lie algebra. The isometry Lie algebra decomposes as a direct sum of as vector spaces of a subalgebra 8 and an ideal N, where H consists of Skew symmetric derivations and N corresponds to translations on the left. This appears on a paper of Joseph Wolf and later in a paper of Wilson in the 80s. And we recall that the Lie algebra is casted nilpotent when it satisfies the condition we have there. So in particular, when we say two-step nilpotent, we will consider the Lie bracket of two elements and then the bracket with another one, and we get 0. And in the case of the three-step nilpotent Lie algebra, we will put one more vector and do the corresponding Lie bracket to get 0. So in the case of nilpotent groups and nilpotent algebras, what we have is the next theorem about Killing vectors and first integrals, or about the isometry algebra and first integrals. So we get from the Lie algebra of the isometry group. So we take a few symmetric derivation plus an element of the Lie algebra, and we consider the first integrals determined by the corresponding Killing vector. So this map is a homomorphism, and when k equals 2 and 3 is a monomorphism. That this map is the homomorphism is a result of Woodhouse of 1975, and there you have the reference. And well, for the monomorphism, we needed the description of the isometry algebra of this proof. I will not write the proof here, but an application of this say the following. If you have an n-dimensional subalgebra, which is abelian there on the isometry Lie algebra, then the functions you have as first integrals will be in involution, and this is what we will look for. So, then that is our main application. The point is that until now, for two-step nilpotent groups, most examples of first integrals were constructed by using Killing vector fields, by Killing vector fields coming from the translations on the left. So the derivations were not explicitly used until now. And the other examples of first integral came from invariant functions. Those many results of that were given by Butler. But we will get an example of a Lie algebra in dimension 5 that is three-step nilpotent and that needed the Skew symmetric derivation. This is the example we have there. As I said, which is an example in dimension 5. And you see the Lie brackets, and that gives you a three-step nilpotent algebra. So here you can compute that the Skew symmetric derivation and the abelian subalgebra of the Lie algebra is generated by E3, E4, E5. And if you compute and you take the set of first integrals corresponding to those vectors and also to the Killing vector for D, then you set you have a set of commuting first integral, which is linear functionally independent. It is a consequence of the theorem above that this is a set that is that gives an integrable system, because you can see by computations that the subalgebra spanned by D, E3, E4, and E5 is an abelian subalgebra on the isometry algebra. And so you get a system as you were looking for. So to study invariant first integrals, we should start by considering the linear ones. The linear ones is just to fix a vector x on the Lie algebra and consider the inner product of y with the vector x. And so it is easy to see that fx is a first integral if and only if the map of x is skew-symmetric with respect to the metric we have. The other examples we can think about is those corresponding to quadratic polynomials, and they are constructed by considering a symmetric endomorphism. So we consider a symmetric endomorphism on the Lie algebra, and we modify the metric by this symmetric endomorphism, and you get a polynomial of degree 2. So this polynomial is a first integral if and only if it satisfies the condition we have there. Okay, at the middle of the slide. So in the case that we have a nilpotent Liouville, then the only possibilities for a linear first integral is to consider that the vector is on the center, and well, you can also specify the symmetric maps for nilpotent Liouville. We will see the formulas later. But in the case, you will always have solution of symmetric map, then, because when S is the identity, you are in the case of the energy function. Well, now the point are the involution of those examples. So we have the Killing vectors, we have the invariant integrals, invariant first integrals that came from linear functions or from the quadratic functions, that is from the symmetric endomorphism on the Lie. So the first result is that all the invariant first integrals Poisson commute with the first integral coming from Killing vectors corresponding to the left translations. Okay, only with those corresponding to the left translations. For those Killing vector corresponding to the skew-symmetric derivation, you should compute that, and we will explain here. So in the case that you are considering two first integrals, then those first integrals are in involution if and only if the Lie bracket of the vector you have is 0. Also, if you have first integrals corresponding to symmetric endomorphism S and T, you get a condition, an algebraic condition for their involution, which is written at the Lie algebra level. And if you consider a linear map and a symmetric endomorphism, so a linear map, a linear function corresponding to a vector field U, and a symmetric map S, then the corresponding first integrals Poisson commute if and only if at U composed with S is skew-symmetric on the Lie algebra N. So all of that gives you algebraic conditions to find the involution condition. And then if you consider now the case of a skew-symmetric derivation, then for k-step nilpotent Liouville, you also have the Poisson commutation, so of ft star with fu with the linear first integral. This is 0 whenever u is in the kernel of D. And when you consider fd star, f, that is the first integral corresponding to the Killing vector field D, and you put the commutation with G's S where S is the symmetric endomorphism, then you can see they are in involution if and only if DS is a skew symmetric map on N, on the Lie algebra. So let us go to the first example on the two-step nilpotent situation, which is already known, that is the Heisenberg group. The Heisenberg group is a Lie group of dimension 2n plus 1, which has a Lie algebra also of dimension 2n plus 1, but with a center of dimension 1. And this center is spanned by a vector Z. So we consider they are the usual metric that makes this basis we are reading there an orthonormal basis. So with help of this metric, you can decompose the Lie algebra H as the direct sum of vector subspaces, the center and the orthogonal complement. And then with that, you can construct the maps JZ that you will read at the end of the slide. So at the left, on the left, you will have an expression on the center because the expression that the Lie algebra is two-step nilpotent says that the Lie bracket is contained on the center. And on the right of the expression, you have the inner product on the vector subspace V. And so the maps JZ you have there are skew symmetric maps on the subspace V. And the point is that those JZ maps describe in general the geometry of the two-step nilpotent Lie group. And so you can see that in the case of the Heisenberg Lie group, if you look for the symmetric endomorphism that gives you first integrals, then you will get the following, that the S should be a multiple of the center on the center, which is spanned by the vector field, by the vector set, and with respect to the vector subspace V, it should satisfy the condition that S commute with J, where J is the map corresponding to set of norm 1. Okay? And that is very nice because this will translate for the general case. But also in the case of the Heisenberg Lie group, we have a better description that say that any symmetric map gives you a skew symmetric derivation, and in such way that the corresponding first integrals Poisson commute if and only if the skew symmetric derivations, the Lie bracket of those skew symmetric derivation is 0 in ISOV. Okay. So this is only possible on the Heisenberg Lie algebra, on the Heisenberg Lie group. But it is a very nice result. In the more general setting, Eberlen, in his study on the integral system, and later Del Barco and Moroyano studied conditions for symmetric endomorphism to give the first integrals, and we see there. So once you have an S, which is a symmetric map on the Lie algebra, this will give you a first integral if and only if you have the conditions above. Sorry, the next condition. The first condition is that the map S should commute with the map JZ for all set in the center. And the other condition is that at of S is skew symmetric on V for all vectors. And well, the work of Del Barco and Moroyano was related to symmetric killing tensors, not only to symmetric killing vector fields, which are symmetric killing tensors are generalization of killing vector fields. Another kind of functions which were given, which are also invariant, were constructed by Leo Butler, and they are in equation 4. So you take also the maps they set, and you consider the even the even composition of this function, they set, and so you get polynomials of different degrees. And the point is that for the different degrees you have, then all these functions, are in involution. So you can ask about the involution conditions of those functions with the functions given by the symmetric endomorphism and by the skew symmetric derivation. And so you get formulas that you can read there. Go there. So in low dimensions, the result or the application we have is that for any k-step nilpotent Lie algebra with k equals 2 and 3 and of dimension at most 5, there exists a left-invariant metric whose geodesic flow is Liouville integrable. And in all cases, those the explicit functions are constructed with killing vector fields or with symmetric maps. Well, that are the results of integrability. And what is nonintegrability? Nonintegrability means that it is not possible to construct such a set of n functions in involution which are linear independent. So results in this direction were given by Butler, which introduced a nonintegrability condition on the Lie algebra. So this nonintegrability condition, which is an algebraic condition, states that once you consider a Lie group n that admits a lattice to construct a compact space, then there is no metric of those left invariant that can induce to the quotient, and so the quotient is has a completely integrable geodesic flow. But the point is that at the Lie group, you can have the complete integrable setting. This is the example of the non-integrable situation, of this non-integrable result of Butler, were given on a Lie group, which is constructed with the three Lie group, two-step nilpotent Lie group in 3 generators. This is a Lie group in dimension 6. So you are able to construct with the tools we were working with a set of 6 functions in involution. Those functions are for the Lie group. But when you consider a co-compact lattice, and so you will translate all the functions to the quotient, then you have problems. And the point is that you will not have the integrability system for the geodesic flow on the compact space. Some more general results were given also by Butler, considering the maps J in general position, that is when there exists an element in the center that has 2 and distinct eigenvalues. And he proved that in this case, the geodesic flow is integrable in the non-commutative sense, but at the same time, Bolsinov and Jovanovic proved that the non-commutative integrability implies the Liouville integrability in the sense we were talking about. So that means that for the previous iteration, we have Liouville integrability, and the construction is explicitly in the paper of Butler. Also in the same paper, he talked about Heisenberg-Reiter Lie groups, and if they admit a co-compact lattice, he proved that the geodesic flow is smoothly Liouville integral. In all these situations and on the compact space, the geodesic flow will be smoothly Liouville integrable because of topological abstractions that were given by Taimanov. And in the case of two-step nilpotent Lie group, it's not possible that the geodesic flow is analytical Liouville integral, because these kind of quotients do not satisfy this topological condition given by Taimanov. So examples of Lie groups that are not contained in the previous example are H-type Lie groups. Well, the Heisenberg Lie group is Heisenberg-Reiter, but the quaternionic one is not Heisenberg-Reiter, and the condition for the H-type Lie group say that the map J is not in general position in this situation. So the situation of the quaternionic Lie group was solved by Tamara and Bauer in an extra paper where they considered and they constructed the Hamiltonian system, and they proved the Liouville integrability in this situation. Well, for the Heisenberg Lie algebra, the geodesic flow, as we say, is Liouville integrable. The first integral came from Killing vectors and from symmetric maps, and the corresponding first integrals are given there. So consider a lattice gamma R on the Heisenberg Lie group. And then, so as I said, the invariant functions are easily induced on the quotient. And for the first integral corresponding to the Killing vectors, there you have problems to induce them. So you should work a little to construct a new first integral, which will be smooth, but not analytic. Here is the formula. The point is that the first integral fx star is not invariant on the fiber, but it is possible to construct a first integral on the quotient. This was analyzed in work of Butler, and also we studied that with Alejandro Coxa and Silvio Reggiani in the paper. In the paper 2 years ago, 4 years ago now. Well, the non-integrability condition of the Lie algebra implies that the Lie algebra should be non-singular. The notion of singularity is that one where you compare the maps JZ. So if all maps JZ are non-singular, you say that the Lie algebra is non-singular. If all the maps JZ are singular, you say that the map that the Lie algebra is singular. And if you have JZ maps that are non-singular and other which are singular, then you have almost non-singular Lie algebra. Here there is mistake. Non-integrable Lie algebras imply that the Lie algebra is singular, not non-singular, sorry. But the converse is not true, and so the counterexample is given with the star graph. So Lie algebra, two-step nilpotent Lie algebra, which is constructed with help of graphs. So it has a two-dimensional center, and it is a Lie algebra in dimension 5, where all maps JZ are singular, but the corresponding geodesic flow, if you do the computation, gives you a complete integrable system. Also, when you consider a lattice, and you are able to induce the first integrals and to prove that the geodesic flow on the compact space, on the corresponding compact space, is complete integral. Well, here are some of the references we were considering along the talk. Some open question we have is that to understand more about nonintegrability and also integrability, to get new functions in involution, to get more tools or techniques to construct first integrals, I think this is not easy, and also to understand more about the algebraic relations we have in the set of first integrals. Okay. So for me personally, the question of non-integrability is a very open problem on how to see that. In any case, two-step nilpotent case, and also in any solvable book. And so I think now, thank you very much for your kind attention.
Thank you for a very nice talk. Are there any questions?
So what happens for four-step nilpotent in the theorem about the monomorphism from the killing vector fields?
I don't know because for the proof of the injective situation, I needed the explicit expression of the killing vector I have. And when I have a fourth step, the formula is very complicated.
So it's not known. It could be true, but it's not known yet. Okay.
Not for me. Not with this proof. I think this should be. They should have another techniques or tools to understand that. And in the work of Woodhouse, he said only about the homomorphism, but I was not able the monomorphism, the injective situation there.
Okay, thanks.
Are there other questions? No. Is the expectation that sort of generically they will not be completely integrable? Or
so I didn't hear you.
Is the expectation that generic for generic metrics that would not be completely integrable? Is that expected, or do you have any intuition there? Or
I don't know. It is also, I think, an open question if is it possible. Until now, in all the results, for the results say for any co-compact lattice, and we have no example where for a lattice you get complete integrability, and for another one, no.
Interesting.
This should be an easier question, but I don't know. As I say, I do not understand very well the question of non-integrability. But all results we have is in the two-step nilpotent case, and this said either you have no integrability, or for all co-compact lattice you will have integrability. So
Let's see.
So I think there are many open questions.
Thank you. Are there any other questions, or if not, thank the speaker again. And our next talk is in 2 weeks, September 30th at 11 p.m. UTC. So much later in the day for most of us. And the speaker will be Ramiro Lafuente. So thank you for joining us.
Thank you.